So, these are some of these sort of philosophical enormities that I think, once you have AIs that can sort of perform, at human level or simulate humans, these are going to be activated.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm continuing my investigation into the so-called hard problem of consciousness. I've spoken to several people who believe that consciousness arose in single-celled organisms and is somehow integrated at higher levels through electrical synchronization or intercellular molecular transport into some sort of a unified experience. Hindus and Buddhists that I've talked to believe that there's a universal consciousness of which we all partake in some way. And this is actually similar in some ways to Sir Roger Penrose's theory of consciousness called Orchestrated Objective Reduction, where microtubule organelles in the brain's neurons have evolved to concentrate this diffuse universal consciousness present in the collapse of quantum superpositions. Some of these folks believe that the randomness at the heart of quantum mechanics is necessary for free will and volition. Others, like Bertrand Russel, believe that we act in accordance with our will, even if our actions have past causes and the future is predetermined. Today, I'm honored to be interviewing an expert who pushes the limits of human knowledge in terms of our understanding of the implications of quantum computing in regards to artificial intelligence. If you like what you're hearing, please press like on your podcast app and share it with your friends. Love to see you on our Facebook group, The Rational View. Scott Aaronson is David J. Bruton Centennial Professor of Computer Science at the University of Texas at Austin, and previously at MIT. He received his bachelor's from Cornell University and his PhD from UC Berkeley. Aaronson's research in theoretical computer science has focused mainly on the capabilities and limits of quantum computers. His first book, Quantum Computing Since Democritus, was published in 2013 by Cambridge University Press. He's received the National Science Foundation's Alan T. Waterman Award, the United States Peace Award, the Tomasani Chisesi Prize in Physics, and the ACM Prize in Computing, and is a fellow of the ACM. Dr. Aaronson, welcome to The Rational View.
Thanks. It's great to be here.
So I've been exploring theories of consciousness and how it arises, and it's such a diverse field. A significant fraction of the people I've spoken with have said that computers cannot be conscious. We need continuous processes. What's your position on the sentience possibilities of artificial intelligence?
Okay. This is the kind of thing you want to take a deep breath before fielding, right?
Yes.
So I will confess that I do not know which kinds of physical systems can and cannot be associated with consciousness. I regard that as not merely a confusing question, but in a certain sense the confusing question. It is or one of the most confusing questions that human beings have ever asked. Right? It has all sorts of obvious moral and ethical implications. At what point does a fetus become conscious? What about a coma patient? What about various animals? What about AIs of possibly the not so distant future? What would be the argument that a continuous process is necessary for consciousness? That what is so special about something continuous as opposed to a digital process?
It's not clear to me what the argument is. I interviewed Dr. Arthur Reber, who's a philosopher who believes that cells are sentient, and he holds that there's a significant difference between a simulation of a cell and a cell. There's the continuous real thing is qualitatively different than a simulation of the same thing. Now I know this kind of falls into the question of artificial realities, and questions about is nature computable, and can we simulate the
Mhm,
world, for
mhm.
example?
Yeah. So I'm not sure that this distinction people want to make between a real thing and a simulation of the thing is really going to answer for us the questions that we want answered, right? Because I mean there were skeptics of AI who would make this point for a long time. They say, well, a simulation of a hurricane doesn't make anyone wet, right? And then to which one might reply, well, what about a simulated person inside of that simulation, right? They would certainly react, within the simulation as if they were getting wet, right? And so, like at what point does the magic pixie dust of reality get imbued into something? When does Pinocchio become a real boy? Right. But I really loved the way that Russell and Norvig approached this issue in their famous textbook on artificial intelligence, right? Where they say, well, it might be true that a simulated hurricane will not make you wet, but imagine someone said, well, imagine someone looked at a calculator and said, obviously, it's not really multiplying the numbers; it's only simulating multiplying them, right? And this would just be nonsense. Like we would have trouble even parsing this because it seems obvious that a simulation of multiplication is multiplication, right? Or you could say
Okay,
that
okay.
the is a simulation of operator just acts identically on multiplication, right? So then the question is, well, what is consciousness? Or like, is it more like a hurricane or more like multiplication? And lacking a theory of what consciousness is, or even less than that, lacking the any agreed upon criteria for identifying what is or isn't conscious. How on earth are we supposed to be able to answer that sort of question?
It's very difficult to have a discussion about something that you can't define. It's a qualia. This is the word that's been invented to make this a hard problem, but you can't distinguish a universe with a qualia from a universe without a qualia, as far as I can tell.
Except that presumably you wouldn't be in the latter because no one would be experiencing anything there. But but yeah, but you could say that the entire way that science has made progress, since Galileo and Newton, has been by setting this kind of question aside, right? By saying we are going to write down a mathematical model of the physical world, to sort of and we're going to we're going to be satisfied if we can predict the appearance of color, if we can predict based on atomic spectra or whatever what is going to appear red or blue, how fast something is going to go, right? We are not going to obsess over, well, okay, but is my red the same as your red, you know and and what is the true experience of seeing red, right? And with those questions, one could argue whether there has been any progress since Democritus very recognizably talked about these sorts of questions 2,400 years ago. Okay. But at least if you put those sorts of questions to the side, then you can make progress. And so then the question is, well, the progress that you make sort of not explicitly talking about qualia or consciousness or whatever, is it ever going to make contact with the hard problem of consciousness, or is that question just in some completely different magisterium, just serenely untouched by all of the ordinary progress in science?
So, yeah, some people would argue that it is an unanswerable question. I think many physicists and philosophers have said that
Yeah,
you cannot answer it,
yeah,
and I'm not of that mind yet. I'm somewhat agnostic, as perhaps you are. That I think let's keep pushing forward on where we can push, and we'll look under the light for consciousness, and until, until we can spread the light a little further.
yeah. Yeah, well, like with every famous unsolved math problem, like the P versus NP problem, is the one that I know the most about, right? But you will get people saying, well, why do you assume that it has an answer? What if it's just independent of set theory, right? And the answer to that question is always, well, ever since Gödel, we can't rule out such possibilities, for any question that hasn't already been answered, just with a few exceptions, like whether white has a win in chess. We know that question has an answer, even if we can't prove it, right? But other questions might just be undecidable, let's say, from the currently accepted axioms of set theory. Okay, but then you have to push back and ask, well, could we prove that? Could we, if you could at least prove that the question is undecidable, then that would give you maybe a meta kind of resolution, right? But and that was done for a few questions. Most famously, the continuum hypothesis and the axiom of choice in the 1960s. But for most of the questions that we care about in math, even if they're independent, we don't know how to prove independence, right? And so I would say the same thing with the hard problem of consciousness. Even if you could just convincingly show that it has no solution, then that itself would constitute progress of a sort. But I don't know how to do that either.
Can we just step back a second? Many of us, including myself, is probably not familiar with the continuation or the continuity.
Continuum hypothesis. Okay, well, so the continuum hypothesis was maybe one of the most famous unsolved problems of mathematics, and in particular set theory. It was posed by Cantor in the late 19th century. So Cantor very famously discovered that there are different levels of infinity, right? So there's the infinity of the natural numbers, 1, 2, 3, 4, and so forth, and you can argue that is equivalent in a sense to the infinity of even numbers, right? In the sense that you can put the two in one-to-one correspondence with each other, right? Like you could marry off 1 with 2 and 2 with 4 and 3 with 6 and so forth, so that every natural number would be matched with exactly one even natural number. Okay, so you can say even though it seems like there's only half as many even numbers than there are numbers. No, those are the same degree of infinity, because the two sets can be placed into one-to-one correspondence. And similarly with the rational numbers and so on. But then Cantor made a very, one of the most shocking discoveries in the history of math, which is that if you look at the infinity of real numbers, like the points on a line, that is a greater infinity. Okay, that cannot be placed in one-to-one correspondence with the infinity of natural numbers. No matter how you try to do it, there will always be real numbers left over. Okay, and this was proved via what was called Cantor's diagonal proof, which then inspired most of the subsequent work in mathematical logic from Bertrand Russell, Russell and Whitehead, the Principia, to Gödel's incompleteness theorem, to Alan Turing's work on computability. Okay, but Cantor made these enormous discoveries. But then he posed the next question, which he wasn't able to answer, which is that there's the infinity of natural numbers, which is called Aleph 0. That's the smallest infinity. And then there's the infinity of real numbers, which is called the continuum, or it's also called 2 to the Aleph 0 power. Okay, so, and that is provably a greater infinity. Okay, he then asked, are there any infinities in between the two? So is there any set which is larger than the natural numbers, but smaller than the real numbers, in its cardinality? Is there any intermediate infinity? And he could not prove or disprove that there was one. And supposedly, he worked on that for decades, and it drove him insane. and he literally died in a mental institution. Okay, but
It's hurting my brain right now.
all right, but then David Hilbert in 1900, when he announced his 23 greatest math problems for the 20th century, the continuum hypothesis was number one. Okay, that was his first problem, and people didn't know what to do with it until finally in the 1930s, Gödel, and this was just some few years after he proved his incompleteness theorem, Gödel managed to show that the continuum hypothesis is which is the statement that there are no intermediate infinities. By the way, that the real numbers are the next bigger infinity after the natural numbers. He proved that that was consistent with the currently accepted axioms of set theory. Okay, so in other words, if set theory itself is consistent, and if you just add in, which by Gödel's incompleteness theorem, set theory can't prove its own consistency, right? But we can assume that it is consistent, right? If you assume that what's called Zermelo-Fraenkel set theory, which is our sort of standard axioms of set theory, is consistent, and then you just add in the assumption of the continuum hypothesis, that the continuum is the next infinity after Aleph 0, then you will not create any contradiction. That will not create any inconsistency. Okay, but then in the early 1960s, another guy, Paul Cohen, proved that if you add in the negation of the continuum hypothesis, that is, if you assume that there are intermediate infinities, then that also will not create any inconsistency. Okay, so in other words, either answer is consistent with the axioms of set theory. So on the basis of the axioms, the axioms of set theory that were accepted through the 20th century, the continuum hypothesis is provably unsolvable. If you want to solve it, then you have to introduce new axioms, and you have to convince everyone that your axioms, really are correct or true axioms. And people continue to argue about it to this day. Okay, so we now know in math that a question that people cared about, can have that sort of an answer, right? And of course, you might wonder whether the hard problem of consciousness is similarly just sort of independent from, sort of all the reasoning that we are able to do as creatures in the empirical world, right? But if so, I wouldn't say that we know that either.
No, that's very interesting. A lot of that's beyond my head, but very, very cool. I know you've spoken with Roger Penrose, or spoken at an event with Roger Penrose, discussing his theory, and I've read his book Shadows of the Mind.
Yes,
and where he argues that you pronounce it Gödel?
Gödel, yeah.
So he argues that Gödel's theorem shows that our thinking is not computable. The process of consciousness is not computable. We are thinking beyond the capabilities of computational systems. What's your response to that position?
Yeah, I don't think Penrose is right about that, to be honest. And I'm not staking out a weird, I would say that almost every mathematician and computer scientist, or everyone who knows Gödel's theorem, who has looked into this, has said no, that this argument just doesn't work. But I will, I'm happy to spell out for you the sort of usual reasons that would be given as to why Penrose's argument just doesn't do what he wants it to do. The issue is that when I'm if I'm observing someone, if I'm looking at a mathematician and saying like, wow, they're doing something really impressive, they really understand what's going on, and they can not only use these axioms, but they can propose new axioms. Right. The truth is, I don't know what's going on inside of their head. Right. I just see their behavior. Right. I see, that they publish these papers. I see that they answer these follow-up questions and so on. And now for any behavior, that I see them doing, including even, inventing new axioms, inventing, new math problems, inventing, radical new mathematical insights. I could imagine an AI that would do the same thing, right? I could certainly imagine programming a computer to have that same behavior. Now, you may have played around with GPT-3, which is, maybe the strongest AI in the world right now, right? It's a text engine, and yeah, it can actually, often, sort of give you a reasonable argument, for, like, similar to what a high school student would give you, maybe. Although if you ask it to justify something false, it will just as happily do that, right? So, it will just sort of run with any premise that you give it, right? So you could say, clearly this is not yet at the point where, it is going to challenge Penrose's thesis, right? Although, it is, it's much more impressive than I expected any AI to be by this point in history. Okay, but now imagine, instead of GPT-3, we have GPT-10, GPT-20, right? And imagine that, you could, interact with it. You could give it a mathematical Turing test, as it were, right? And it will just, act, indistinguishably from, the most brilliant human mathematician that you know, right? And so then, you would say, well, is set theory consistent, right? It would say, well, set theory, I can, from within the axioms of set theory, you can't prove, its own consistency. But yes, I believe that it is consistent, right? Because I have some intuition for it. And now the truth is, a human mathematician wouldn't have been able to tell you anything better than that, right? That's just the same as a human mathematician would have been able to say. And you could imagine some, machine learning procedure that would learn to say the same thing when asked the same question. Okay, and so now, in order to say why that doesn't count, Penrose is forced to retreat to some kind of internal criteria. Okay, so he's forced to say, well, the AI might say that it believes that the axioms of set theory are consistent, or, that they have a model, or whatever, but it doesn't really mean that, right? It's just, parroting, what was in its code. Whereas when I say that, I really mean it. I can just see all the sets just sort of laid out there in my mind's eye. I can see that set theory is consistent, right? And okay, there are a couple of problems with that, right? One of them is, in the past, humans have thought that they could just see intuitively that some axioms were consistent and have been wrong about it, right? Maybe the most famous example was Frege, right, who, like, wrote this whole treatise on foundations of arithmetic in the late 1800s. And then famously, the entire program was killed by Bertrand Russel, right? When Russell asked, well, what if we define the set of all sets that do not contain themselves as members, right? Which was a thing that you were allowed to do in Frege's system, right? And then you could ask the question, well, does that set contain itself as a member, right? And if it does, then it doesn't. But if it doesn't, then it does, right? And that killed, that killed the entire system that Frege had labored on for a decade or more. Okay, and Frege, to his credit, immediately admitted that and said, okay, my whole and I was talking about
Wow.
Zermelo-Fraenkel set theory, as like the standard foundation of math from the 20th century. That was sort of born out of the ashes of the death of Frege's program, right? The whole point of this Zermelo-Fraenkel system was to sort of avoid the contradiction that comes in when you talk about the set of all sets, or things of that kind. Okay, but the truth is that the greatest human logicians on earth at the time missed this, right? They missed that there was this inconsistency in the system, until Bertrand Russell noticed it. Okay, so, and there are many more contemporary examples, right, where people conjecture that some axiom is consistent, and it turns out not to be. Okay, so our experience is that humans do not have some kind of supernatural insight. There are people, of course, who are more brilliant than others at math. There are people who are, for just about any of us, there will be people who will maybe seem magical to us because they will be so much more brilliant than us. But then those people will also make errors, right? Those people will have other people who they look up to as more brilliant than them. Okay, so now if you want to say, well, I can just see that a model of piano arithmetic exists, or a model of set theory exists. I could just see it intuitively. I mean, it becomes an unfalsifiable claim. It becomes the same sort of argument, as if someone had said, well, an AI might say that it enjoys the beauty of a poem, or it enjoys strawberries with cream, or whatever, but it's really just saying it, right? It doesn't really have qualia, right? But in that sense, in that case, I would say, well, then why not just go back to the original argument that people have been having for thousands of years? Why even bring Gödel's theorem into it, right? Why not just talk about strawberries and cream?
Mm-hmm. That's good. That does bring it back to a reductio ad absurdum. I mean, intuition is good as far as it can be backed up by calculations, because otherwise you could be wrong.
Yeah. I mean, look, one could imagine where Penrose, or some version of Penrose, was able to make a case, right, where that would be really like a sword in a stone, right? Humans would be King Arthur, right? They can pull the sword out of the stone. They can just do this demonstrable task that an AI just provably cannot do, or provably would need astronomically greater time to do, right? So you could imagine, like, for example, if humans were able to reliably solve some kind of really hard computational problem. In computer science, we talk a lot about NP complete problems, right? Where you might have an exponential space of possible solutions to search through. And a good solution if you find one, right? But there are just so many possibilities to check. And a huge fraction of what we want to do in computer science, from training a machine learning model to optimization to breaking cryptographic codes, or mining Bitcoin, or can be reduced to these kind of NP problems. That's what they're called, problems where there are exponentially many possible solutions, but you can verify a good solution if someone shows it to you. And now imagine that humans were able to reliably solve those problems, and imagine that we could prove that a computer needed an exponential amount of time to solve it, right? Then that would be a sword in the stone test, right? That would be the sort of thing that I imagine Penrose could then seize upon, right? And say, you see, right? This is the task that separates humans from at least any currently constructed computers, at least any computers that are based on the Turing model, right? But we don't know of any such example, right? In fact, humans, cannot reliably solve these NP complete problems, and for most examples, like finding the prime factors of let's say, of a huge number, or finding the shortest route that visits a whole bunch of cities. While we don't know of a provably efficient method, even on computers, I would much rather give that problem to my computer than try to do it myself, right? Or try to do it with pen and paper, right? So it's very hard to sort of point to a clear separating example of that kind.
So, in your opinion, then, and is there any evidence that would distinguish classical computing from quantum computing in the realm of human cognition, or can we even tell whether we're using quantum mechanics, or is there any magic there?
Oh, well, okay. So, well, I mean, of course, this is what most of my work has been about for 20 plus years, about quantum computing and in what, ways can it outperform classical computing. I the to tell you in one sentence, yes, we now believe that there are clear domains in which quantum computing can exponentially outperform classical computing. And as far as we know, none of those domains have anything to do with human cognition.
Okay, that's fair.
Okay. The examples where quantum computers, can get huge speed ups, we think, over classical computers. Well, there are a few of them. Okay, the original, and maybe still today, most important one, practically, is just simulating quantum mechanics itself, right? Like if you want to know the rate of some chemical reaction, or you want to know, the behavior of some new material, right? A quantum computer, of the sort that many companies are now racing to build, could be an incredibly useful tool of discovery for those sorts of things. It could help in potentially, designing new drugs, designing, new photovoltaics, high temperature superconductors, right, which are all quantum mechanical problems at the core, right? So, maybe it's not surprising that a computer that itself is quantum mechanical could help with that. That was Richard Feynman's original idea when he introduced quantum computing in the early 80s. But now the discovery that really got everyone excited about quantum computing, sort of put it on the map, was Peter Shor's discovery in the mid 1990s that a quantum computer could also quickly find the prime factors of huge composite numbers. Right. So, if I give you a composite number that is, let's say, n digits long, right? If you tried to find, and I asked you to find its prime factors, if you tried to do that by just testing one divisor after the other in a brute force way, that would take time that would be exponential in n. Okay. So, if n is in the thousands, that could easily be longer than the age of the universe. Now, we do know factoring methods that are better than that, but they're still pretty slow. The best ones that we know use time that's like exponential in the cube root of n, okay, or something like that. And so, because factoring is believed to be a hard problem, we use it as the basis of much of the encryption that currently protects the internet. Okay, so anytime you order something from Amazon, or you send your credit card number online, or in fact you visit any website with HTTPS in the URL, and you see the little padlock icon on your web browser, right? Your information is being protected by, well, one of a few cryptographic codes, but which are based on things like the hardness of factoring numbers. Okay, the believed hardness. And what Shor showed is that if you could build a scalable quantum computer, then that would no longer be true. Okay, so he gave an algorithm on a quantum computer, which that didn't exist at the time, and still doesn't exist at the level that we would need it. Okay, but he gave an algorithm that would factor an n-digit number using only about n squared operations, something like that. Okay, so he showed that if you could build a quantum computer with thousands or millions of what we call qubits, which are quantum mechanical bits that can have superposition of zero state and one state. And if it worked according to textbook quantum mechanics, if it works like the theory says it should, then you could use it to factor numbers quickly, and thereby break most of the encryption that currently protects the internet. Okay, so that was a tremendously exciting discovery, and that's really what started quantum computing as a field, and started the quest to actually build practical quantum computers. Since then, people have discovered other applications for quantum computers. including a Grover's search algorithm, which is, anytime you have like a list of n possible solutions to some problem, could be like an NP complete problem, or, a search or optimization problem. And, you know how to recognize a solution if you find it, so like classically, if you knew nothing else, then you just be doing pure trial and error. And, it might take about n steps until you find the solution, right? Maybe n over 2 steps on average, right? If you're just guessing them randomly. Okay, what Grover showed was that a quantum computer could find the solution with only about the square root of n steps. Okay, so compared to Shor's algorithm, this had an enormously greater range of applications, right? It's not just so Shor. What Shor did was extremely specific to factoring numbers and a few other very, very special problems in number theory and group theory, right, where we really had to take advantage of the structure of those problems. It was not just a simple matter of you just try all the possible divisors in superposition or something like that. If it were that simple, you wouldn't have needed Shor to think of it, right? So Shor's algorithm was this exponential speed up, but for these very specialized problems. Grover's algorithm is for an enormous range of practical problems, but the speed up is not exponential. The speed up is only by the square root. Okay, so and the square root of like 2 to the 1,000 power is 2 to the 500 power, right? It's still pretty big, right? So Grover's algorithm would give you something, but it would not sort of move problems from this sort of exponential time family to the linear or quadratic time family. Okay, it wouldn't do that much. So what we learned early on was that even quantum computers would have limitations, right? There would still be problems that would be hard even for them, but there would also be some problems that are exponentially hard classically, but that allow these remarkable quantum mechanical speed ups. And now you could say, well, where exactly is the line between the two, right? Like, for which kinds of problems can we expect quantum speed ups? And that is an enormous question, one that we've been working on for the past 30 years, right? The answer to that question is not a sentence; it is, an entire field of study, right? Just like classical algorithms is an entire field of study. Okay, but now your question was about, what does any of this have to do with human consciousness? And I would say the answer is far from obvious, right? I mean, for a couple of reasons, right? One of them is that, I would say that there is no physical evidence that the brain is that any animal brain, including the human brain, sort of is operating as a quantum computer, right? What we see when we look at the brain is we see, neurons, which, there are billions upon billions of neurons, connected by synapses, and but the neurons, each neuron is itself quite complicated, but it seems complicated in basically classical ways. And in particular, once a neuron either fires or does not fire, that seems like a classical event, right? Like it doesn't, a neuron does not go into a superposition of firing and not firing, right? And in fact, if it tried to do that, then that superposition would not survive for more than the tiniest fraction of a second. Okay, and the reason is that the brain is a very sort of hot, wet environment, right? It is no place for a qubit, right? You wouldn't expect a quantum system to be able to maintain its state for any appreciable amount of time without, in effect, being measured by its environment, sort of, leaking or becoming entangled with its environment. These are all different ways to say it. Okay. Now, like when people are trying to build quantum computers now, right, they are, doing things like, taking superconducting, coils, Josephson junctions, they're called, putting them on a chip and then cooling that chip in a dilution refrigerator to like 100th of a degree above absolute zero.
Right. And that's just to keep them from in this quantum superposition.
Right, right. And even, right, that's right, in order to maintain the quantum superposition of the qubits. And even then, that's not called enough. Okay, that's not keeping the qubits alive for as long as we want them to stay alive, right? That's just what a commercially available dilution fridge will give you. Okay, so you're entering a regime which seems, of physics, which seems very far removed from biology. Okay, but then the other thing is that even supposing that somehow the brain were able to do quantum computation, it's not clear how much that would be good for. Like, suppose that you had a superpower of simulating molecular dynamics and of breaking the HTTPS encryption that protects the internet, right? How much survival value do you think that would have had for your ancestors on the African savannah, right?
The fact that we haven't been able to find, a lot of application of this quantum computers, like, when they were first posited, it was like this magical thing that's going to solve all of our problems. We'll superimpose everything. It'll come to a solution.
Right. Well, you have to distinguish how it got written about in the press from what the experts understood. Right. And, a lot of what I've been doing on my blog, frankly, for the past, 16 years has precisely been trying to bridge that gap. It's been just trying to, take like, no, we don't think a quantum computer will just solve NP complete problems by trying all the answers in parallel. And, and just saying things that are obvious to everyone who works in this field, right? They're not even controversial. But then when you say them to the public or to business people or to investors, then it's news. It's news to them because they were led by a lot of irresponsible hype to expect something totally different.
You feel these are real limitations and not just the fact that we haven't come up with the right algorithms. You think that there is no real magic here?
Well, that's a hard question because the truth is that, like, we don't even really understand the limitations of classical algorithms yet, right? So this is what this famous P versus NP problem. That's exactly what it's about. Right. So, like, could it be that for all of these NP problems, meaning all the problems where you could quickly recognize a solution if you were shown one, that there is actually a fast algorithm to find the solution, even on a conventional computer, right? That might sound fanciful, and yet no one has ruled it out, right? That is the P versus NP problem, which I would say is a math problem that is sort of defining for the 21st century, at least as much as the continuum hypothesis was for the 20th century.
And that's right. Basically, the traveling salesman problem. The salesman has a set of cities to visit, and you have to do it in the shortest period. And the more cities you get, the more complex the solution has to be, and the more space you'd have to look at to solve the problem.
Exactly. The traveling salesman problem is one of the most famous examples of what are called the NP complete problems, which are the problems in NP which sort of capture the entire difficulty of the class NP. If you can solve them, if you can solve any one of them, then P would equal NP, meaning that you could efficiently solve all NP problems. Factoring is not believed to be NP complete. That's why Shor was able to give a quantum algorithm to solve it, right? By taking advantage of very special properties that it had. Okay, so for the NP complete problems, we don't know whether there is a fast quantum algorithm. We don't even know whether there is a fast classical algorithm. Okay, we know that quantum computers could give you the speed up of Grover's algorithm, which is this modest sort of square root speed up. We don't know whether they could generally do better than that. Okay, so these are all enormous unknowns. Okay, but I like to say that if we were physicists instead of mathematicians, computer scientists, we would have just declared P not equal to NP to be a law of nature. We would have just said, this is an observed fact about the world. We're going to assume that it's true, until some revolution comes along and tells us otherwise, right? It seems like the entire software industry for half a century or more has been looking for faster ways to get approximate solutions to combinatorial problems, right? And no one has ever found anything that would sort of bridge this divide. And so whereas if indeed it's not possible, then we understand a lot about why we haven't been able to prove it yet, right? There are just immense difficulties in sort of proving a negative, proving that there is no fast algorithm to do something. Okay, but you're right. You're right. I mean, the truth is that sort of in the I talked about this sort of black box world where all you know how to do is guess a solution and check whether it's valid or not. Like within that world, we know that Grover's algorithm is the best that even a quantum computer could do. Okay, but in the real world, you always know more about your problem than that, right? Like if I give you a traveling salesman problem, right, you're able to do more than just guess a route and then see like is it short enough or not, right? You can make part of a route and then backtrack because it doesn't look like it's right. You can do all kinds of you can have a route that is not quite right, but then you can make little local improvements to it, right? You can play all kinds of tricks. And so, are there any tricks that will let either a classical or a quantum computer solve those sorts of problems much faster than how we currently know? You're right. These are enormous problems. These are what sort of keep us employed as classical and as quantum computer scientists.
So, assuming then that consciousness and our minds and everything that we're doing is we know the physical laws. There's no evidence that the physical laws are being broken. There's no evidence that there's a soul behind this or magic or something doing this. So, assuming there is no magic, and assuming that we know the rules pretty well, we just haven't been able to prove it, how does this then affect your moral judgment on AI? When do we have to start treating our AIs as beings?
Yeah, these are that's an enormous question. I would say that my sort of first intuition when I try to think about this, is very close to Alan Turing's, as which expressed in his epical paper in 1950, Computing Machinery and Intelligence, right? Which this is the paper that proposed the Turing test, right? That basically said, look, if there is a being who you can interact with, from behind the screen, or let's say, we would say today, like in an online chat, right? And if this being is totally indistinguishable to you, from a human, right, by any test that you can devise, right, so that you are, just you will swear up and down that that it is a human, then why aren't you morally obligated to regard it as if it were a human, right? And ultimately, like people treat this as like a metaphysical argument, or they get obsessed with kind of the details of how this imitation game, would actually run, right? But I feel like at its core, it's really a moral argument, right? It's like, like if the being on the other side of the screen turns out to be made out of silicon rather than out of carbon, why is that more relevant than, let's say, the color of a person's skin? Why is it more relevant than whether they're a male or a female, right? And of course, Turing faced enormous discrimination, because of being gay, right? And you can even, if you read his 1950 paper, you can see places where he's alluding to that, right? And and like why, like we've sort of, a large part of the moral struggle of humanity, over the millennia has been to sort of widen the circles of empathy, to say that just because something looks different, right, if it is going to act like a sentient being, then we are morally obligated to treat it as a sentient being, right? So I feel like that intuition has an enormous amount of purchase on me. Okay, but having said that, there would be one at least very important difference between an AI and at least any currently existing humans, and which does seem morally relevant. Okay, and the difference is simply this: with the AI, you could make a backup copy, right? You could copy the code somewhere else, and then you could say, well, okay, now is it murder if I delete a copy, if I can just restore it from backup, or is it only murder if I delete the very last copy, right? You could say, I'm going to rerun, this AI from the same initial condition, right? So like you could say, so suppose that you simulated torturing an AI. That sounds like a really bad thing to do. But suppose that you then rewound it. You then just deleted that entire interaction and you just reset it to its initial condition. Now, did the bad thing you did to the AI, the torture or whatever, did it ever happen? Right? There's no record of it anymore.
We don't understand consciousness enough to make these judgments.
No. I mean, these are right. And yet all of these sorts of questions seem morally relevant now, right? Or like let's say that the way that my computer works, in order to just have some redundancy, it runs every computation 3 times and takes the majority vote. The computer on the space shuttle, I think, did something like that, right? Okay, now have 3 consciousnesses therefore been brought into existence, right? Or is it only one, right? How do I decide when a second running copy of this AI counts as a second consciousness, a second observer, right?
Well, we had the same problem in our brains. We're bilateral brains, and they can operate independently as independent consciousness if you break the wires between them.
Yeah, right. And now if we have to worry about trolley problems like people do in ethics, like should I sacrifice one person in order to save 10 other people, right? Well, now I need to know how many copies of this AI have actually been brought into existence by this, and one can even ask stranger questions. So there was a revolution in cryptography 15 years ago when it was discovered how to do something called fully homomorphic encryption. Okay, and what this means is we now understand how to do arbitrary computations on encrypted data without ever decrypting it. Okay, and this could,
wow, cool.
Right now it's pretty slow in practice, but eventually this could have all sorts of applications in cloud computing. Like you want Amazon, AWS to do a huge computation for you, but you're very worried that they're going to snoop on it, right? We now know how to give them encrypted data that they can compute on and be none the wiser about what they did for you. Okay, but now. Here's a thought experiment that was due to actually a student of mine, Andy Drucker, right? Suppose that we took a simulation of a person, so a consciousness, right, and we ran it in a homomorphically encrypted form. Okay, so we ran it in a form, where all of the information, about the state of the brain is encrypted. And as we do the simulation, it all remains encrypted. And let's say that the decryption key is in another galaxy or something, right? It's just not available, right? So now we can say, has a consciousness been brought into existence by this totally encrypted computation that is completely meaningless to everyone in this galaxy? Right? Does it only become conscious if we go and retrieve the decryption key from the other galaxy? Okay, so these are some of these sort of philosophical enormities that I think once you have AIs that can sort of perform at human level or simulate humans, these are going to be activated.
These sort of questions bring up. I don't know if you're familiar with Daniel Dennett's approach to consciousness. That it's not a thing. It's a post hoc rationalization, right? And that process almost that viewpoint almost seems to be necessary when you start getting to these problems.
Yeah, well, you could say, well, okay, so I think the challenge now becomes, if you want to say that there is something special about the brain that is going to differentiate it from all of these computer simulations that you can play all of these weird games with, right? Then now the burden is on, the believer in the brain specialness, right? They're the one who has to articulate what is it that is different about the brain, right? Why isn't it just a meat computer, right? And I think the closest thing to a potential answer to that I have been able to think of, right? And I'm not sure whether I believe it, but like this is the kind of thing that a principled answer might look like, is to say, well, maybe it is just physically impossible to make a good enough copy of someone's brain, right? Maybe, if you wanted to make a good enough copy of you, let's say, good enough to instantiate a second copy of you, or duplicate your identity or whatever, then you would actually have to scan your brain all the way down to the molecular and atomic level. Okay, but in some sense you can't do that because of what's called the no cloning theorem in quantum mechanics, right? That you're what'll be more familiar to most people is probably the uncertainty principle, right? That if you try to measure the exact quantum state of all of the molecules in the brain, you'll actually necessarily change those states, right? And so then you might say, well, in order to make a good enough copy of your brain, maybe you would necessarily have to destroy it in the process. And so then, if so, there is a kind of privacy or uniqueness to an individual human identity, that an AI program would not have, because you could always just freely copy the AI program, right? So so ironically, this would not be kind of a positive thing that would distinguish humanity, right? Like a task that we can do and that the AI can't do. This would be a negative thing, right? This would be something that cannot be done with us, but that can be done with the AI.
You're going to have to bring the evidence for that.
Yeah, right. But now, like, is that actually true, right? Like, so it is also plausible that maybe you could like, yes, it would be technologically very challenging to scan the state of someone's brain and make a duplicate of it. But you would only have to be looking at the classical level, right? You would just need some nanobots that would just scan, let's say, the strength of every synapse and the connectivity pattern of the neurons, and that would be good enough, right? So and I think probably most people who think about this would incline toward that latter position. But I would say, like, if I were really going to believe in ineffable human specialness, right, then this is the kind of question that I would be looking at. Like, can you actually physically copy the state of someone's brain, without destroying them in the process, right? Like, this is a question where, unlike the hard problem of consciousness, it seems like we could actually learn something, right? Like, progress in neuroscience and chemistry and physics could actually tell us more about this. And this does seem somehow relevant to what we wanted to know.
I've talked to some people that are doing experiments on quantum information processing and superpositions, and I've talked to people that are looking at polarized electron spins in fruit flies, and there's a lot of really cool stuff going on right now, and I'm really excited to follow along with that and just see where it goes.
Yeah. So I would say that there is a lot of evidence that quantum effects are important in biology and in various contexts. I mean, green plant photosynthesis relies on quantum tunneling effects. Bird sonar relies on apparently some quantum entanglement effect in some molecule in the bird's inner ear.
Wow.
Right?
Cool.
European robins. Particular, right? So people have found all of these cool things, right? But they're all kind of at the molecular level, right? Which is what you would expect. At the molecular level, kind of everything is quantum mechanical. So why wouldn't natural selection find ways to exploit that, right? And it looks like indeed it does, right? But then
And whether or not that's important for consciousness or not is also a good question.
exactly. But then is any of that actually relevant to consciousness? That is a much, much harder question.
So we're getting to the end of our time slot. I really appreciate you coming on and chatting with me about this stuff. Really mind-bending. I love the perspective and the clear articulation of what we don't know and what we do know. And I think that's very helpful. And so for coming on, I'm going to send you a Rational View t-shirt. Really appreciate it. One last question for you. I ask a lot of my contributors, what kind of science fiction are you interested in?
Oh gosh. Well, I loved Asimov as a kid. Yeah, I read all the Asimov that I could get my hands on. And these days, I sometimes, I feel like studying science has kind of ruined science fiction for me to some degree, right? Like as soon as I see them say something that I know is just absurdly wrong, or that no scientist in that situation would ever say, then it's hard for me to stay inside of the story, you know. But I love any kind of science fiction that plays things for laughs. And this, I was a huge fan of Futurama, the science fiction cartoon show, right? I love that. And I also enjoy just fiction about science and scientists, when it's funny and it's well written, like The Big Bang Theory, for example. I confess that I enjoyed.
That was fun. A good depiction of that level of interaction. The scientists actually, typical their personal interactions and getting into that. It was fun. Yeah. So thanks so much for coming on. Appreciate chatting with you.
Well, thank you. I enjoyed talking.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.